Okay, I'm Sanat Kumar. I have 15 plus years of teaching as well as industry experience. Okay, so today I am going to explain you about what is VLSI. Okay, you should have the exposure of what is VLSI. Okay, and what are the job opportunities in VLSI that I am going to explain. So basically, what is VLSI, I'm going to explain. Okay, so just I'm sharing my screen. I'm sharing my screen. See here. So basically, so what are the job opportunities? Okay, so we are Gnanodaya VLSI Technologies. We are there in Bangalore as well as Hyderabad. So what are the job opportunities in semiconductor industry? Okay, so job opportunities, if you see, okay, before that I want to tell about VLSI. After that we'll go with the job opportunities. Okay, so VLSI is nothing but what VLSI is a very large scale integration. Okay, very large scale integration. Okay, very large scale integration. So here, previously we have some 10 modules or 100 modules, means with a man, we can, please mute yourself, please mute yourself. Okay, yes. So here, please mute yourself. Somebody is. Hello, ma'am. Hello, ma'am. Just who is unmuted? Mute him. Harsha, mute yourself. Yes. Please don't unmute in between my session. If there are any queries or doubts after completing the session, just I will ask you. You can means you can give the in chat box. Okay, you can give your queries in the chat box. Okay, so VLSI is nothing but very large scale integration. So basically there is like a small scale integration, SSI, MSI, and LSI. Okay, there is a VLSI. So VLSI is nothing but we are integrating some millions of transistors in a single IC, that is nothing but VLSI. Everywhere is VLSI. Everywhere, if you see, so from day one onwards you are using VLSI. So that means in household applications you are using VLSI. Okay, ACs, your LED TVs. Okay, LED TVs, and next whatever the household applications are there. Please mute yourself, please. Hello, Anjali ma'am. Hello, Amruta. Mute yourself. Okay. So here, VLSI. So VLSI, basically there are two types are there. So that means VLSI is nothing but you are integrating the millions of transistors within an IC. So you can integrate some thousands of modules in that VLSI. So everywhere is VLSI. In automobile, VLSI is there, medical domain, and wearable devices, and wherever you see you have VLSI. Okay, so the VLSI circuits are everywhere. So VLSI is basically divided into two types. One is front end, and next one is back end. Okay, in back end, so in front end you will get RTL design. Okay, RTL design, and you have design verification. Okay, design verification, and you will get DFT. That flow I will explain, don't worry. So back end means you will get physical design, PD flow, and analog layout. Okay, analog layout, all these you will get in backend. Okay, so backend means they will design the circuit, they will make the ICs, they will design the ICs at backend. Front end means basically will write the program. Okay, so VLSI is everywhere. Suppose you are using microprocessors in your laptops, or microcontrollers in specific applications like ACs, refrigerators, or washing machines. Okay, in automobiles you are using this one. Okay, everywhere is VLSI. Okay, so if you see microcontroller, so microcontroller, you already studied about microcontroller and microprocessor. So microprocessor means basically in your laptop you are using this laptop or desktop, which will do some specific general purpose operation. That is nothing but microprocessor. Microcontroller means it will do some specific application. Okay, it will do some specific application. That is nothing but micro controller. Okay, microcontroller have some inbuilt RAM, ROM, some IO or I2C protocols, I2C bus, some all are inbuilt. Okay, this is SOC. SOC is nothing but system on chip. System on chip. Okay, you are using some mobile phones, no? Who is unmuting? Please mute yourself. Amruta? Amruta? Hello, Amruta? Yes. Please don't unmute. After completing the session, just I will ask any doubts. The doubts you can post in the chat box so that I will clear your doubts. Okay. So system on chip. System on chip means you are using your mobile phone, no? So in mobile phone there is a like system on chip, that is Qualcomm Snapdragon. That is a processor. So all the peripherals like I2C or AMBA protocols, RAM, ROM, all are there in this IC. Okay, that is nothing but system on chip, and FPGA. FPGA is nothing but field programmable gate array. Okay, field programmable gate array. Okay, field programmable gate array, that is nothing but FPGA. Okay, so this we can program. So these are the target devices for VLSI. So basically so here we are the VLSI engineers. What we'll do, we will make we will make the brain, means we will make the chips, and these embedded engineers will use the chips. Okay, we are making the brain of that computer, and embedded engineers, they will use that, they will program that chips based on the application. Okay, so microcontrollers, if you see, so as I told you, that CPU, ROM, serial, RAM, timer, all in a single IC. That is nothing but microprocessor. This is microprocessor. You have external CPU. Okay, external CPU, ROM, RAM, serial, all are externally available. Like if you see some your desktop or laptop, so all the memories and RAM, ROM, serial IO ports, serial interface, all are externally interfaced. Okay, and microcontroller means all are inbuilt. Suppose if you take 8051 microcontroller, it consists of some inbuilt RAM, ROM, and inbuilt UART. All the some peripherals are there in the microcontroller. So microcontroller is used only for the specific application, whereas microprocessor is used for the general purpose. So like if you are using computer, laptop, okay, we can use multiple operations. Okay, that is microprocessor. Okay, this is microprocessor. So clock frequency for microcontroller is, it ranges from 1 megahertz to 300 megahertz. Okay, and here for microprocessor it will be, clock frequency will be more, 1 gigahertz to 4 gigahertz. Okay, this is microprocessor, and this is system on chip. System on chip is nothing but like you have ARM processor. As I told you, system on chip is Qualcomm Snapdragon. Okay, that is system on chip. Okay, so you have ARM processor. Okay, ARM processor will be there. Okay, and inside there will be PLL, oscillator. Okay, these are some USART, universal synchronous asynchronous receiver and transmitter, SPI. Okay, two-wire interface, ADC, CAN protocol. This is mainly used for automobile. Okay, USB drive, PWM, synchronous, SRAM, flash. All are connected with the AHB or APB bus. This is nothing but we call as AMBA bus. So through AHB bus and APB bus, this is connected. So many peripherals are there in a system. This is acting as a system on chip. Okay, in microcontroller also Raspberry Pi is there. Raspberry Pi is acting as a system on chip. Okay, Raspberry Pi is acting as a system on chip. Okay, that is system on chip. And next, FPGA means what? Field programmable gate array. Field programmable gate array means it consists of like CLBs, configurable logic blocks. Okay, this consists of configurable logic blocks. We can program this FPGA. Suppose if you want to design some FSM, finite state machine. Okay, so finite state machine, we can design, and we can port this code into the FPGA, so that our FPGA work based on the FSM. Okay, if you want to design a sequence detector, sequence detector using FSM. So you can write the program, and by using Xilinx Vivado in the Verilog you can write, and you can port into this FPGA. Okay, so this is FPGA. So basically, like this design flow is there. So basically, the detailed design flow I will show you. 1 second. The detailed design flow is here. 1 second. 1 second. Okay, this one. Detailed design flow. Here it is there. Okay, this is the ASIC. Okay, so basically ASIC means what I will tell you. So basically I told you, no, so VLSI is divided into two parts. One is front end and back end. front end front end and back end. Okay, so front end means first design specification. Suppose any client is coming. Okay, when any client is coming, he come up with his requirements. Okay, so like suppose if you want to design any half adder circuit, half adder, how many inputs and how many outputs? Two inputs and two outputs, no? Half adder have two inputs and two outputs. Okay, so that means the client will come with what is the behavior of this circuit. It will add two inputs, and it will produce two outputs, sum and carry, based on this 0 0 0 1 1 0 1 1. Based on this it will produce sum and carry. So that means we need to find out how many number of inputs and how many number of outputs, and how many types of modules we need to use. Okay, that will come under the design specification. Okay, next we need to do architecture means what? Architecture means we need to do planning. Okay, we need to do planning, where the, like, if you want to design CPU. Okay, CPU, so client is coming, I want this CPU to design. So CPU consists of what? ALU, and control unit, and memory unit. So where you need to keep ALU, where you need to keep control unit, or where you need to keep this memory unit. Okay, that placing, that whatever the planning is there, that will come into the architecture. And micro architecture also. Micro architecture means you need to design for ALU, you need to design for control unit, and you need to design for MVU, memory unit. This is nothing but micro architecture. Each one is nothing but we can call as IP also. IP means what? IP means intellectual property. Okay, each module we can call as IP also. Okay, after that there is a RTL design. RTL design means what? Basically we'll write the program in Verilog language, Verilog HTL. We are writing the program in Verilog HTL. So basically, like what is RTL means what? RTL means register transfer level. Okay, transfer level. So register transfer level means what? Register transfer level means this will shows how the data is transmitting through the to this registers. Okay, so basically there are four types of modeling styles are there. Switch level modeling, and next you have logical level modeling, and data flow modeling, and behavioral modeling in the Verilog. Okay, so basically RTL coding means that means we are using this data flow modeling and behavioral modeling. By using RTL design, we are using this Verilog HTL. We can convert whatever the design into hardware. That is RTL design. Okay, RTL design means RTL engineers are there. They will write the program. For these IPs. Okay, these individual IPs, they will write the program, and RTL engineers. Okay, after that, if design is met, so it will go to the next step. So suppose you designed a half adder circuit. Okay, so that means you are getting for A and B, you know that sum and carry, sum 0 carry 0, sum 1 carry 0, and sum 1 carry 0, sum 0 carry 1. You know by using truth table, but how the design will know? Okay, how the design will know? So design will know, so we need to verify the circuit. Okay, so by using RTL also we can verify, we can write the test benches. But up to small designs like FSMs, okay, up to FSMs we can verify the circuit. Suppose large designs are there, like SOCs. Okay, large IPs are there. Okay, with Verilog it will not support. Okay, and so it will not support. So you need to go for what? Other language, that is nothing but SV, System Verilog, or UVM. System Verilog is it's a designing language. It will support 30% of 30% of design, and mostly 70% we are using for verification. Okay. And UVM is nothing but, this is not a language, this is nothing but a methodology. This is the methodology. So we are using system verilog in the UVM. System verilog, universal verification methodologies. Okay. So here, who are the engineers? That is DV engineers. Design verification engineers. Design verification engineers, what they will do, whoever the RTL engineers will write the program, they will write the program, they will, these DV engineers will verify this circuit, whether each and every corner cases they will check. Okay. So why? Because so before that we need to verify. Suppose like so many chips we are using in aeroplanes, okay, or in rocket launching, so many chips we are using. Suppose if there any bug is there, what happens, it will be lost to the total aircraft, and as well as it will lost to human beings also. Okay. So before going the chip into the market, we need to do so much verification. Who will do means design verification, these DV people will do. So basically they will use the two languages, that is nothing but SV and UVM. Okay. If design is met, it will go to the next step, and if design is not met, it will go to the RTL design. Okay. So these both will work together. Okay, this both way, this RTL engineers and design verification engineers will work together. Okay. So this is what this is about the this one. And if not met means what, it will go to the RTL. If design is met, okay, if the design is met, that means whatever the specification is there, that is proving, okay, with the verification. Okay, verification as well as design. Okay. If design is met, okay, goals, whatever the goals design is met, it will go to the next state. Okay. Logic it will go, the synthesis engineers are the synthesis engineers. Synthesis engineers means what is synthesis? Synthesis is nothing but the name synthesis is nothing but whatever your program is there, that you are converting into gate level netlist, hardware gate level netlist. Okay. Gate level netlist. Okay. So that means here by using synthesis we can convert this one into hardware, and we need to do some constraint. They will work on some constraints. What are the constraints? Like area constraints, power constraints, or timing constraints. Okay. They will do some constraints. Okay. They will do some constraints on this logic synthesis. Okay. After that, DFT means what? Design for testability. DFT means design for testability. Okay. Design for testability means what? They will see for some test cases, some techniques are there, DFT engineers will do. BIST, okay, scan test, or random test. Okay, they will use some test cases to the design, and they will see the functionality of that design. Okay. So who will do means DFT engineers will do. Okay. So basically in VLSI you have first RTL engineers. Okay. RTL design, so RTL engineers are there, and next DV engineers are there. Okay. DV engineers are there, and synthesis engineers are there. And next you have DFT engineers are there. Okay. DFT engineers are there. Okay. So till here this is nothing but VLSI front end. So whatever the design and verification is there, that will come under the VLSI front end. Okay. And next you have LES. Okay. And next there is a static timing analysis. STI is nothing but static timing analysis. Okay. STI is nothing but what? Static timing analysis. Static timing analysis means what? You are like there are like setup time and hold time are there. You are dealing with delays, timing parameters. Okay. So that means in terms of nanoseconds. Okay. You are dealing with the timing related parameter, that is nothing but STA. Okay. In STA there are means pre-layout STA is there, post-layout STA is there. Okay. So pre-layout STA means before after synthesis you have pre-layout STA. Okay. Static timing analysis. Okay. There are some techniques are there with that static timing analysis. Again STA engineers are also there. STA engineers. Okay. STA engineers. If design is not met, it will go to logic synthesis. If design is met, where it will go? PD flow. PD flow is nothing but back end, physical design, okay. In PD flow you will get like floor planning, routing, okay, routing and routing, clock tree synthesis, okay, clock tree synthesis. So basically we'll use this PD flow. We are using cadence tools, okay. We are working under 17 nanometer technology, okay, 17 nanometer technology, okay. So technology means like if you see the MOSFET, there is a channel length, no. So channel length, so that means here this is source and this is drain and source. What is this channel length? That is nothing but technology. Now now our India is developing the ICs with 2 nanometer technology, but we are working in 17 nanometer technology, okay. And parasitic extraction is nothing but we need to remove some capacitors or inductors, okay. That is nothing but what parasitic extraction, okay. And after parasitic extraction you need to do post layouts, STA static timing analysis also you need to do. Post layout STA you need to do. If design is met, it will go to the next step, and if the design is not met, again it will go to the PD flow, okay, physical design flow. And physical verification you need to do, okay. So in the front end you need to do RTL verification, and after design in the back end also you need to do physical verification. So here physical verification engineers are required, okay. Physical verification engineers, PD engineers, back end PD engineers are required, okay. And next, so here there is a file called GDS2 file, okay. GDS2 file will be generated, okay. Graphical system design like this, GDS file will be generated, that is given to fabrication. So in the fabrication what they will do with some techniques like photolithography, like diffusion and implantation, okay. There are techniques like N-well, okay, N-well technique. They will design the CMOS circuit, okay, N-well technique, twin tube technique, okay. They will do the fabrication, okay. So this is about the total ASIC flow. Okay. Did you understood any? Yeah. Shall I move forward? Yes. Did you understood? Yes. Give thumbs up. Yes. Shall I move forward? Okay. Okay. Next you see. So next, so what are the target devices in ASIC and VLSI are target devices in VLSI are ASIC and FPGA. ASIC and FPGA. So what is ASIC? ASIC is nothing but application specific integrated circuit. Okay, integrated circuit. So application specific integrated circuit means once it is used for only specific application, okay, it is used for only specific application. Once the program is written, so you can't change your ASIC, okay, you can't change your ASIC. So many applications are there. So your mobile phone is there, mobile phone is one ASIC, okay. Why it is ASIC? Mobile phone is ASIC. Suppose you purchased your mobile phone with suppose 16 GB of RAM and let us take so 16 GB of RAM and 8 GB of 16 GB of internal memory and or 64 GB. Nowadays you are using 64 GB, 8 GB of RAM you take. So nowadays 16 GB also we are using, okay. So what happens sometimes like if future increases, like if you want to use 128 GB or if you want to use 32 GB, can we update this? We can't update, okay. So we can't update, that is nothing but ASIC. So like ACs are there, AC, refrigerator, okay, and refrigerator, microwave oven, okay, and in automobile airbags, okay, automatic means auto locking airbags, auto locking braking system, okay, and engine control system, okay, for costly car. So that these ICs are used only for specific application, that is nothing but ASIC, ASIC. Okay, in ASIC also again there are two types. One is full custom ASIC, and next is semi custom ASIC. Semi custom, full custom ASICs are nothing but what, so here they will fabricate this their ASICs from the scratch. Okay, suppose semi custom ASICs means they will use this standard cells. Standard cells are predefined cells already available, and they will use in their design. Okay, so I will tell you with the example. Suppose full custom ASICs are there. Full custom ASICs means I will tell you with suppose your phones are there. Suppose iPhone is there, iPhone, or Samsung is there, Samsung. Okay, these are full custom. Full custom means they have their own ICs, own ASICs. Okay, so here what happens for iPhone and Samsung, within 1 year one model will release, and cost is also more. It is 80K to 1.5 or 2 lakhs it will be there. Okay, cost is more. Okay, and semi custom means what? Semi custom means suppose if you take other phones like MI or Oppo. Okay, Oppo and Vivo, these phones are there, no? So these phones are semi custom. So what they will do, they already, suppose MI phone is there. MI phone, what they will do, they will take processor from Qualcomm. They will purchase these whatever the peripherals from the so these are nothing but IPs which will be developed by other countries, other industry. Okay, other industry, they will do this IPs, and they will make assemble. Okay, so that means long run these are standard, these long run. So here it will be like useful for only 5 years, like that. After 5 years the problem will start. Okay, in semi custom ASICs. Okay, so that is ASIC. Okay, and FPGA is nothing but basically field programmable gate array. So where you are using this FPGA means so once for the ASIC, once the program is written we can't change. Okay, that is only used for specific application. Suppose like nowadays we are using 5G, no? 5G. Okay, some mobiles are there, so that will support only 3G. Okay, suppose like Geo is there. Okay, so Geo is providing only 5G. Okay, so what they will do, they will decrease the speed of this 3G. Okay, and they will give the speed to 5G. Okay, any 3G person will come and he will ask that I am using Geo, I am not getting speed. Okay, so what they will suggest, nowadays mostly majority of people are using 5G technology, so you need to upgrade your mobile. Automatically this person will, so in order to increase his speed, you need to upgrade from 3G mobile to 5G mobile. Here also ASIC means what, that 3G mobile is made only with supporting 3G related network only. Okay, it is not supported with 5G. Okay, so that is nothing but ASIC flow. It is only used once the program is written, and they can use in bulk production. Okay, it will take low power. Okay, and they will use for bulk production. Okay, that is nothing but ASIC. Okay, FPGA is nothing but we can use this FPGA, we can reprogram this. Okay, this is reconfigurable. Okay, suppose like where you are using means, suppose cell towers are there. Previously cell towers are working on 3G and 4G. Okay, nowadays they upgraded to what, 5G. So in future suppose 6G is coming. Okay, 6G is coming means what, every time, so any new technology, this 6G is coming, they need to reprogram from 5G to 6G. So in that they use this FPGA, field programmable gate array. Okay, I am telling with the real time examples where you are using this VLSI in real life examples. I am telling with the examples. Okay, so every concept you need to correlate with the example, then you can understand the concept. Okay, so this is about ASIC and FPGA, and this is Xilinx FPGA flow. So basically we are using Xilinx Vivado. So previously Xilinx is one company, so now this AMD is one company which acquired by Xilinx. Okay, now you have a tool called Xilinx Vivado. Okay, Xilinx Vivado. So in Xilinx Vivado, what you are doing, first you will writing the program in Verilog or VHDL. Verilog or VHDL. Okay, again after that we are converting this we had a tool is there, no, this tool will convert HDL code into schematic. I told you, no, there is a synthesis is nothing but what, by using synthesis we are converting the schematic into netlist, gate level netlist. Okay, after that we need to do implementation. Okay, we need to do implementation based on the FPGA target board. Okay, and after that we need to do some floor planning, routing, placement and mapping. Okay, that will be done in the implementation, and after doing this implementation there is a bit file will be generated. Bit file is nothing but what? Bit file is nothing but it is in terms of zeros and ones. Our every electronic device will understand only zeros and ones, no? So bit file will be generated, that will be port into that my FPGA. Okay, so this is like, see here, HDL source we are writing in either Verilog or VHDL, After that you are making synthesis. After that, so your synthesis means what? You are converting your Verilog HDL into gate level netlist. Okay, after that you are doing implement means what? In implementation you are translating, mapping, placing and routing. Okay, after that bit stream generation is happening, and this you are porting into FPGA. Okay, this is FPGA, normal FPGA flow. Okay, so these are the design closures, like functional coverage. Functional closure means by simulation we can see the functionality of circuit. Okay, by in the form of waveforms we can see this functional closure. Okay, power closure means we need to see some timing closures or power efficiency. Okay, to minimize the power consumption. To minimize this power consumption we are using power closure. Functional closure means we are checking with simulation. Power closure means we need to see for timing related, and timing closure means what? We need to go for static timing analysis. Okay, STA. In STA again there are two types are there: pre STA, okay, pre layout STA and post layout STA. Okay, and CDC is nothing but clock domain crossing, and different clocks are coming. So suppose clock should be distributed to different modules. Different modules are operating in different clocks. Okay, there you need to have the clock domain crossing, CDC, and reset domain crossing also. Reset domain crossing means there are two types of resets are there: asynchronous reset, okay, and synchronous reset. Okay, so here asynchronous reset is nothing but what? This reset is synchronous to the clock. Okay, suppose if you take active low reset means when you design a D flip flop, so here active low reset means what? It is going to where this is nothing but this is a active low reset. This is let us take so active low, this is active low reset. Okay, active low reset, this is reset mode, this is functional mode, and this is nothing but reset mode. Okay, so here in synchronous reset both are synchronous with the clock. Okay, synchronous, when the clock is changing then the output is changing. This is nothing but synchronous reset. Whereas asynchronous, so both are synchronous. Whereas in asynchronous reset, here reset mode, functional mode, and again reset. Okay, reset up, here reset removal. This is nothing but reset removal. This is nothing but reset applied. Okay, reset removal is synchronous, but reset applied is what? Asynchronous. Basically we are using this asynchronous reset only. Asynchronous reset in our design. Active low reset we are using. Why? Because when the power is shut down, we are applying, this is in reset mode only. Okay, if it is active high reset, what happens when the power is there? It will go like this. So that means this is reset mode, this is active high reset. We need to give extra power in the reset mode. That you will study in the RDC, reset domain crossing. Okay, reset domain. So clock related issues you will study in clock domain crossing, and RDC, reset domain crossing, reset related issues you will study in the RDC. Okay, reset domain crossing. Okay, so basically this is front end course. front end course. Front end, you have two courses are there. That is ASIC RTL design. ASIC RTL design. Okay. ASIC RTL design means we will teach digital electronics. This is the basic subject, and we will teach Verilog and some Verilog projects. Okay. STA, so static timing analysis, clock domain crossing, and reset domain crossing will teach, and linting also will teach. Okay. So basically this is RTL design, ASIC RTL design. Okay. If it is a DV, design verification, if it is design verification, so you need to see about, you need to study about system verilog. For verification purpose, I told you, you need to study about SV and some assertions. Okay, assertions, and you need to study about UVM. Okay, universal verification methodology. Along with the verilog, here up to verilog we will teach. After that we will teach system verilog assertions, and UVM will teach. Okay, that is nothing but DV. This is nothing but DV. Okay, design verification. Okay, this is the course overview. And basically what is the difference between Verilog and VHDL, if you see. So the difference is, so here what is HDL? HDL is nothing but hardware descriptive language. Hardware descriptive language. Okay, so what is the difference between high level language and HDL? High level language like C, C++, Java, okay, and Python. Okay, Python, these are high level languages. Okay, what is the difference means, here they will develop the application. They will develop the application only. Okay, they will not develop, they will not make the hardware, but by using HDL we can generate the hardware. That is the only difference. Okay, and Verilog and VHDL, basically VHDL is a very high speed integrated circuit hardware descriptive language. So hardware descriptive language means, suppose you have half adder, so you will draw the diagram of half adder, you will write the truth table. Okay, you will write the truth table, that is 0 0 0 1 1 0 1 1. You already studied in digital, no? 0 0 1 0 1 0 0 1. So you know the operation. So this operation you are writing in terms of textual format. Textual format is nothing but HDL. For hardware also you need to have some programming language, no? That programming language is Verilog and VHDL. Okay, so basically VHDL, they came into market around 1999. Okay, so this is mostly used in defense. And academics also they will use. Okay, this is hard syntax is there. Okay, this is controlled language, and this is hard to learn, and multi-level abstractions are available. Okay, suppose if you want to write the basic AND gate. Okay, now if you see the Verilog, it will follow the olden language like Ada or Pascal. Okay, this language, it is very complex. Okay, very complex language. Okay, whereas Verilog, it is high level HDL, it will follow C syntax. If you are comfortable with C, you can easily learn the Verilog. Okay, this is easy syntax, easy to learn, and multi-level abstractions are available. Okay, so here just I'm giving the difference between this VHDL and Verilog. I'm writing the program for basic AND gate. Okay, how many inputs are there? 2 inputs are there. And how many outputs are there? 2 outputs are there. Okay, A and B. Okay, one output is there, that is y equal to what? A and B. Okay, so if it is VHDL, how I write? First I need to initialize. For initialization purpose also, I need to use header file, library IEEE, use IEEE std logic 1164 entity logic port. Okay, end logic, and next I need to give architecture. Okay, in the architecture I need to write the basic logic. Okay, so how many lines of code it is there? 1 2 3 4 4 5 6 7 8, nearly 10 lines of code is available. Suppose if I am writing with Verilog will start with the module, this is the module name, we can call as module name or identifier. Okay, these are the port list. I can give the inputs within the bracket only, bracket also. Okay, I'm using, so that means module and identifier. So module or identifier, what I'm giving, and underscore get input a comma b, output y. Input a, these are the inputs, input a comma b, output y. And I'm using a continuous assignment statement, that is assign y equal to a and b. This is a logical operator, logical and. By using logical and, I'm giving and end module. How many lines of code it is there? Same functionality. With Verilog it is taking 3 lines of code, with which VHDL it is taking 10 lines of code. So now you tell me which one is easy. Verilog is easy. Verilog is having easy syntax, easy to learn, and multi-level abstraction, and this is universal. Wherever you go, corporate people will use Verilog. Verilog for development. Okay, either ASIC. Okay, ASIC they will use this Verilog. FPGA also they will use Verilog, FPGA. Okay, some defense related projects means they are using FPGA, and they use this VHDL. They will use this VHDL. Okay, so this is the difference between Verilog and VHDL. Okay, so this is about this one, and next. So you have like physical design also there. Physical design means what? Suppose if you want to build any like building, okay, so like what they will do, like suppose civil engineer is there, first they will do planning, no, okay, based on the planning they will construct the building. Okay, so planning will be done, and after that they will make some pillars, basement. Okay, after that they will make some pillars. After that, they, with the help of pillars, they will construct walls, and after walls they will make a slab. Okay, and after making that slab, what they will do, they will do some wiring inside, electrical wiring inside that. Okay, after that they will do some painting. Okay, and they will do some placement also, where the like suppose they are constructing some double bedroom flat is there, so where the hall should come, where the bedroom should come, okay, where the kitchen should come, like that. Based on that planning, they will do same. Like that you are making an IC. Okay, so we are making one IC. So what happens, when you are making one IC, so these physical design engineers will take the input from the front end engineers. Okay, they will take the input from the front end engineers. What are the inputs? These are the inputs. Okay, so I told you, gate level netlist is nothing but .v file. Okay, and constraints means I told you, by using synthesis, what they will do, with some constraints, area related constraints, timing related constraints, or power related constraints. After after synthesizing this area, power and timing, they will generate one file, that is nothing but HDC file. Okay, synthesis people will develop this HDC file. Okay, and logical library file, some standard libraries are available. Okay, those are nothing but live file. Okay, multi voltage design files, that is UVF file, and physical library, some predefined library files are available, that is LEF files. These all are the input for PD. What is PD? Physical design. Okay, physical design. So here you are doing floor planning. What is floor planning? Floor planning is nothing but you need to plan your floor, how the die size estimation. Die is nothing but it will be like silicon die is available, like they will make the silicon die. It's like a wafer, a silicon wafer, like it's like a CD, or we can call as a paper, thin material will be there, and they will cut like this. Okay, they will cut like this, and they will make this die. Okay, and where the IO, input output, and macro placements. Suppose here, if you see, these are the output for physical floor planning. Okay, here RAM is there. Okay, RAM 1, RAM 0 is there. Here some more modules are there. So like this, you need to do some from planning, power distribution, the floor planning. Okay. So what are the goals of floor planning? All macros in place grid, no macro overlap. Okay. No PG nets, DRC. Okay. So like this, these are the goals for floor planning. Okay. And these are the input for our PD. Floor planning full chip. So full chip, if you see, these are corner cells. Okay, corner cells, and these are IO cells. Okay, and bond pads, IO ring, core power. Okay, these are some chip floor planning. Okay, so you can study, if you take PD, you can study all these things, IO planning. Okay, floor planning elements, like core area, where is the core area. Okay, so core area is nothing but where the standard cells or macros can be placed. I told you standard cells, no? Standard cells are nothing but predefined cells. Suppose like AND gate is there, AND gate, or like D flip flop, or adder circuit, full adder. Okay, who will make that standard cells? These TSMC is there, no? Company TSMC. Okay, some companies, they will make this standard cells. They will make the standard cells, so we can make use of that standard cells. So what is the advantage of the standard cells means we can decrease the time to market. We can decrease the time to market. Okay, decrease the time to market. So where the standard cell to place, and how the diode size should be there. Okay, how this includes the core area, where the core area. Okay, so like that is the floor planning elements. Okay, placements are nothing but where you need to place the macros in this. Okay, these are the this is nothing but exact location in the core area. Okay, all the standard cells called placements. Okay, so whatever the core area is there, this core area is there, no? So these are nothing but we call as placements. Okay, and next clock tree synthesis is nothing but you need to do by using static timing analysis. You need to do like there is a like universal clock or master clock. From the master clock, each and every module will not operate with same clock, no? So there should be some clock divider circuits that will divide the clock, and that will be given to each and every module. That will be done by clock tree synthesis. Okay, CTS. Okay, CTS. Routing is nothing but basically you need to do some connections you need to do. Okay, that is nothing but routing. Okay, routing. And the sign off checks means you need to do for electrical sign offs, so physical verification, crosstalks. Okay, you need to go with these things in the sign off checks. Okay, so this is about the basic physical design. So basically, like if you see here, basically companies, so there are three types of companies are there. Product based companies. Okay, there are three types of companies are there: product based companies, service based companies, and EDA companies. Okay, EDA means what? EDA. Okay, EDA means electronic design automation. Electronic design automation. Okay, first I told you like LSI. Okay, MSI and this is SSI, MSI, LSI, and VLSI. Suppose you have like 10 to 100 modules, 100 modules in that. So like some small amount of transistors are there. Manually we can do some verification, but some thousands of modules are available. Okay, millions of transistors are available. Manually it's not possible to verify that circuit. Okay, you need to do the help of EDA tools. Suppose if you go for front end, you have like for writing RTL code, you can use Xilinx Vivado, and we can use Quartus Prime. You can use Synopsys VCS tool. Okay, this you can use. Okay, and for verification, some tools are available, like you have Costa Sim. Okay, For verification, basically you are using Costasium and Synopsys. By using Synopsys tools also you can do verification. Okay, Synopsys tools and Cadence tools also. By using Cadence tools also you can write the program. Okay, Cadence tools also you can write the verification. You can do the verification. Okay, and in the back end PD you can use Synopsys tools. Synopsys tools, you can use Cadence tools also. So Cadence, in our institute we have Cadence Innovus tools for PD domain, physical design domain. So what happens, these EDA tools, or we can call as CAD tools, computer aided design, computer aided design. Computer aided design, here this will not work automatically. We are the VLSI engineers, we need to give some guidelines to this EDA tools. We need to give some guidelines to this EDA tools so that this EDA tools will work. Okay, so that means what are the EDA companies? These companies will provide the EDA tools. Okay, Cadence, Mentor Graphics, okay, Synopsys, these are nothing but some EDA tools. Okay, so here so these are the product based. So here what happens, this EDA product based companies and service based companies, they will synchronous up, and that means what, they combine to meet the technology delivery. Whatever the chip they want to deliver, they are using they are making this chip to release into market with the support of whom? VLSI engineers. To the support of VLSI engineers. Okay, so what are the, so here if you see what are the second, what are the service based companies and product based companies, I will show you. See here, so if you zoom this, some product based companies means what, they will produce their own ICs, they will produce the products. Okay, like Samsung, Intel, TSMC, okay, Micron, okay, Qualcomm, Nvidia, Broadcom, MediaTek, TI, okay, AMD, Infineon, Apple. I told you, no, Apple is a product based company, they have their own ICs. Samsung also they have their own ICs, they will produce their own ICs. Okay, ST, okay, and NXP, unlocked devices, these all are total 25 product companies, 25 product based companies are available. Okay, so product based companies are available, and service based companies means they will not produce any ICs, just they will give the service to this product based companies. Okay, so whole thing the product based companies will not do, they will give some task to the service based companies. They will take, these service based companies will take some money, and they will give the service, they will use this manpower, and they will use this they will give the service to product based companies like SCL Technologies, Mindtree. Okay, some companies, you know, I think so, ESG Global, this is there in Hyderabad. Okay, Sankalp, so most of the companies are there in Bangalore also. Mirafra is there in Bangalore. Okay, Chrysemi, okay, Tesolve, Capgemini is there. Capgemini is there in Hyderabad as well as Bangalore. Okay, this is also service based companies. Okay, now Infosys have the VLSI division. Wipro also having the VLSI division. Okay, apart from this, around 100 plus service based companies are available in the Hyderabad, Bangalore and Noida and all over the India. Okay, so these are the listing companies like you know, Intel, Qualcomm, Synopsys, Mirafra, AMD, Moschip, HCL. Some companies, you know, no? Most top companies. Okay, top companies, you know. So these are the some hiring companies of VLSI engineers. Okay, so here if you see the eligibility, one second. Yes. Okay. Till now, is it fine? Any queries or any doubts, give thumbs up so that I will move forward. Yes or no? Shall I move forward? Okay. Okay. So here criteria. Suppose what is the criteria means, you need to be graduated from BE BTech. Okay. So you can join in final year also. You can join in final year, or you can join in 3-2 also you can join. Why? Because what happens, the course will be 6 months. 6 to 8 months it will take. Okay, so course will be 6 months. So what happens after completing your BTech, you will learn all the skills and you will be industry ready. You will don't waste the time for taking the course. You will be industry ready. Okay, so BTech, EC, Triple E are eligible. Why? Because the basic subjects you are going to study is analog electronics and digital electronics. Okay, some TICL, okay, and RTL, okay, and next STA. Okay, so this you already analog electronics means PN junction diode, MOSFET, and CMOS. Okay, these are the levels. So okay, digital means you will study about the number system and those K maps, combinational circuits, sequential circuits, FSMs. Okay, all this you will study. So here what you will do, you already studied this. You have the knowledge in the BTech. Again we will brush up the concepts. Again we will brush up the basics. Okay, so in order to go into the study about core related subjects, you should have the basic fundamentals that we will teach you. Okay, again we will teach you. Okay, you can be ME or MTech, that will be VLSI or electronics. Okay, so why it is EC and Triple E means you already study in your BTech. Okay, so suppose if you take like mechanical or civil, they will not study digital electronics. No, again that will be new for them. Okay, so whether you are already studied, again we are teaching means you are comfortable with that. Okay, minimum you should have 60% score. Okay, good communication skills. Okay, communication skills are required. Okay, the training process will be like this: first registration. Okay, there is a discussion on fee and course. Okay, you can discuss with our HRs. Okay, you can discuss with our HRs. And the training period, mostly training period will be 6 months. Okay, so preparation with mentor support will be there. Okay, there will be mentor support will be there. And conducting mock interviews. Okay, so every week we'll conduct assessments, mock interviews. Okay, and seminars, assignments, to see your capability after completing any concept. Within that week, in that week only we'll keep these mock interviews, assessments, seminars or assignments we'll keep, and 100% placement assistance will be given. Okay, so this is the training process. And basically we are giving in 4 domains also, like ASIC verification, and we are giving same ASIC RTL design also we are giving the course. Okay, so here PD, if you see, course duration is 6 months, daily 1 hour class and lab practice will be there, and weekend batches 6 hours per week will be there. The number of students are 15 to 20. VPN lab support will be there, and whoever the trainers in Gnanodaya, those are 15 plus experienced trainers are available. 100% placement support will be given. Okay, and whereas analog layout is 4 months only, same 1 hour batch, if it is weekend 6 hours per week, so 15 to 20 VPN support will be given, and 15 plus industry experience and placement support will be given. Same ASIC verification also, 4 months of training, daily batch 1 hour class, weekend batch 6 hours class. So maximum will take this intake 15 to 20. VPN support will be given, 15 plus years of experience, and 100% placement support will be given. Okay, so basically fees is like this is old fees. Now fees is 85,000 for all the PD, analog layout and ASIC design. Fees is standard 85,000. If we make some MOU, we will give some discount from this fees. We will MOU with college. Okay, some bulk students are coming, suppose like 20 to 30 students or 50 students are joining, so we will give some discount in that fees. Okay, that will speak with your college, and we will give some that is nothing but a memorandum of understanding that will give some discount. Okay, so basically this is the contact number, you can note down contact number, and this is email, and this is our website. App is also available in the Play Store. In the Play Store, app is also available. You can search with Gnanodaya VLSI. That app you can download, and you can ask for any queries or any registration process. Our HRs will respond. Okay, so this is about VLSA session on front end, back end, and about Gnanodaya. Okay, I want to show some more like we have some webinars also. Uh, uh, so companies, these are the companies, hiring companies, top hiring companies for the placement, multinational giants like Intel, MediaTek, Qualcomm. Okay, EDA companies like Synopsys, Cyient, Ambient, India startups, Desolve. Okay, service based companies, HCL, TCS, Sankalp, Wipro, Capgemini, UST Global. Okay, these all are some top companies. Okay, so these are the students who recently placed in our from our Gnanodaya. He is Amar Gopal. He placed in Apex. Okay, and Ram Babu placed in Capgemini. Sham LNT. Okay, and here Skylight, design Ravi Kumar design verification. Reshma HCL. Okay, and Gaurav Sava. Okay, Delancey. Okay, Capgemini. So these are the some of the students, successful students. They took the training in our institute, and they successfully placed in our company in the different service based companies and product based companies like that. Okay, yes.